Second speaker is Benjamin Siskind from TUV. Benjamin got Frontier 2025 Frontiers of Science Award with Patrick Lutz sitting over there, and he's talking about Martin's conjecture. Please welcome Benjamin.
Yeah, thank you so much for inviting me and for being here. So yeah, I'm going to talk about Martin's conjecture. Again, yeah, joint with Patrick Lutz. So I'm going to give you an overview of what Martin's conjecture is about. I think it'll have some unfamiliar terminology for many of you, so I'll try to spend a lot of the time like explaining the statements of the conjecture and the interest in the conjecture, and then I'll say a little bit about our results. Okay, so here's just some background. So Martin's conjecture is a statement really about computability theory, or sort of at the intersection of computability theory and set theory. So what is computability theory about? Well, many different things, but one thing it's about is studying the structure of the Turing degrees. And the Turing degrees are just the complexity classes of different decision problems, but maybe not quite in the sense of complexity that you're used to. So I'll tell you specifically in a little bit. So okay, this computability theory studies the Turing degrees. It studies also the functions on the Turing degrees. And one observation that comes out of computability theoretic practice is that the natural functions on the degrees seem to have significant structure that's so far sort of not satisfactorily explained. So Martin's conjecture essentially is a proposed explanation for this apparent structure. Okay, very roughly, and this is the part where things are sort of undefined, and I'll explain them to you in a bit. The conjecture is that the only reasonably definable functions on the Turing degrees are minor variations of sort of trivial functions, like the constant functions in the identity function, and generalized iterates of the Turing jump. Okay, so that's the big picture. So computability theory has its origins with Turing's discovery of the halting problem. So there's a decision problem that cannot be decided by a computer program. So here's a way of saying the halting problem. So the problem is to decide whether a program phi halts on some input. In the parameters, the program and the input. And that's not decidable by a program. That's Turing's result. And we can look at a minor variation of the way of phrasing this. So we can fix an enumeration of all programs enumerated by the natural numbers, so phi sub e for e a natural number. And then you can rephrase the halting problem and really Turing's proof in the following way. So here's a minor variation, the halting problem star. Decide whether phi e halts on input e, halts on its own input. So Turing's proof that the halting problem is undecidable really shows that this problem is undecidable. Okay. And moreover, using our enumeration, we can code the halting problem or think of the halting problem as just being a set of natural numbers, which we call zero jump. So zero jump is just the set of all e such that the eth program does halt on its input. So we can take the problem and code it as a set of natural numbers, and so we'll sort of think about the complexity of problems as sort of being described by complexity of sets of natural numbers. Okay. So again, Turing's result says there's no program phi which on input e decides whether or not e is in zero jump. So we can rephrase this problem about membership in a problem about deciding membership in some set of natural numbers. Many other natural decision problems, like the word problem for groups or many other things, were shown to be unsolvable in this way, not solvable by a computer program, by reducing the halting problem to p in some sense. So p is shown to be undecidable by showing that the halting problem reduces to p. So we can phrase this reduction in terms of some generalized version of programs. So oracle programs, where we're allowed to ask for answers to instances of some other fixed decision problem P as part of our program. So here's a definition of the fundamental notion for today. So it's the notion of complexity that's studied in computability theory. It's again different from like computational complexity that you might be familiar with. So for P and Q decision problems, we'll say that P is Turing reducible to Q, written in this way. If there's an oracle program which can solve P given Q as an oracle. So you can solve P as long as you know how to solve Q. You know, still using a program, but you need as input how to solve Q. Okay, and similarly, we say P is Turing equivalent to Q if they're reducible to each other in this way. Okay, and the Turing degrees are just the equivalence classes under this notion of equivalence. So the complexity notion here is, can you solve one problem using a program which has access to the answers to some other problem? Okay. Okay, so we're going to have to code things a little bit. So as we saw with the halting problem, and it's easy to see for many other problems that you're probably familiar with, you can code up problems by sets of natural numbers so that the problem is equivalent to a problem that's just asking about membership in some set of natural numbers. We have sort of normal form for problems given some effective coding. So we're going to start just assuming all our problems have the following form. They're of the form P sub A for A, a set of natural numbers. And the problem P sub A, the decision problem P sub A, is just decide whether or not some natural number E is in A. Okay? And I'll be a little sloppy and just treat these as equivalent even for things like the halting problem in zero jump and things like that. Okay, so we can start talking about Turing reducibility and Turing degrees as being about sets of natural numbers, not just about problems. Okay, and something I'll do a couple times. So we'll let 0 denote just some trivial problem. For example, deciding if some number is in the empty set. So which we obviously, it's just we know how that's going to go. That's going to always be no. So rephrasing a little, Turing's result, the undecidability of the halting problem, just says that this problem 0 is strictly Turing below 0 jump. That's a formal little way of saying 0 jump is not computable. The halting problem is not computable. Okay? But also this result relativizes to oracle programs using other oracles. So the halting problem for programs which use P as an oracle is not solvable via a program which uses P as an oracle. So again, fixing an enumeration that I'm going to label the same way of oracle programs and letting phi E superscript A be a running program phi sub E with oracle A. In that way, we're getting an enumeration of the oracle programs that use A as an oracle. We can let A jump be the sort of coded version of the halting problem relative to A. So the halting problem, A jump is just the set of all indices for oracle programs such that the oracle program with oracle A halts on, each oracle program with input A halts on input E. So it's just, we took the ordinary halting problem and now we're using A as an oracle, whereas before we had no oracle at all. Okay? So this is the relativized version of the halting problem. Okay, so Turing's theorem relativizes in the following sense. So for any set of natural numbers A is strictly Turing below A jump. Put another way, A jump is not, or the halting problem relative to A is not computable via a program which uses A as an oracle. But formally, that's how we'll start writing it. Does that make sense? Any questions? Okay. So again, natural problems are typically shown to be unsolvable by a computer program by showing that they reduce the halting problem in this sense, often in much simpler senses of reducibility. So here's a question: is there an unsolvable problem P such that zero jump is not Turing reducible to P? So the natural ones, this is how we typically reduce, how we show that they're unsolvable. But is there one that's not like this? Well, yes. So this is a question towards the beginning of computability theory, and it was answered by Kleene and Post, and they showed more. In fact, there's an unsolvable problem P that's strictly Turing below. Sorry, did I? Sorry. Yeah, that's strictly Turing below zero jump. So it's not just not above zero jump. It's strictly below. I won't really talk about it. Things could be like sort of off to the side as well. But this we're getting actually strictly below. Okay, so that's the Kleene-Post theorem. And yet this answer is at odds with the empirical observation that natural decision problems seem not to be of this form. So the Kleene-Post proof is some kind of construction where you have in mind this goal of producing something that's like not computable, but strictly below the jump, and you do a sort of diagonalization type construction to exactly come up with this kind of object. Whereas, arguably, this is not a natural procedure. On the other hand, the natural problems that we encounter in practice don't seem to be like this. Okay, so the question is sort of what's going on? What's going on? Is there anything we can say to justify our empirical observation that the natural things are not like this? Okay. Well, one feature of natural decision problems is that they often relativize in a way very similar to the way the halting problem relativized. But that's not going to be enough. So the Kleene-Post theorem relativizes as well. So here's the relativized version of the Kleene-Post theorem. For any set of natural numbers A, there is another set of natural numbers B that's of intermediate Turing degree between A and A jump. So it computes A doesn't compute it. It's computable from A jump, the halting problem relative to A, but it doesn't compute the halting problem relative to A. Okay. So relativizing doesn't doesn't explain what's going on with the natural decision problems. However, the proof of the Kleene-Post theorem does have a feature that natural problems don't sort of seem to have. So natural problems seem to be Turing invariant, whereas all known proofs of the Kleene-Post theorem produce non-Turing invariant witnesses. So what does Turing invariant mean? It just means you map Turing equivalent sets of natural numbers to Turing equivalent sets of natural numbers. So you're sort of preserving the complexity in the sense of Turing computability. Okay, so this is really as I said at the first slide, this is the thing that Martin's conjecture and the talk really are mostly about, are going to be about Turing invariant functions. Okay, so maybe Turing invariance is what corresponds to these observations about natural problems. So here's a slightly imprecise version of a question of Sachs. It's just, can we get a Turing invariant solution to a Turing invariant function sort of witnessing the Kleene-Post theorem? So is there a simply definable Turing invariant function that's always taking a set A to a set F of A that's intermediate between A and A jump? So we know there is some intermediate set, but is there a Turing invariant way to do this? Okay? So that's Sachs's question approximately. And this question is open. A negative answer would explain the empirical, seem to constitute an explanation of these empirical observations about natural problems that I've been talking about. Whereas a positive answer would seem to require like very new methods in computability theory. Yeah, question? That's what I'm being imprecise about. I hope I can. Yeah, we'll see. It's the Sachs's question. This is supposed to be what's called a CE operator or something. I don't even know the lingo. But if we'll consider the case that it's like Borel in a moment. Yeah, I'll explain. That's coming up, I promise. Okay. Okay, and again, Martin's conjecture is going to be a kind of ultimate generalization of a negative answer to this problem. And that's supposed to be, again, an explanation of what's going on with these natural invariant functions, or natural problems. Okay, so let's see some examples of natural problems, or Turing invariant functions. So arguably constant functions are natural. I think it probably depends on the constant, but constant functions are natural. So we're just constantly putting out some fixed set of natural numbers. The identity function is natural. Okay, what else? So the Turing jump, I think, is natural. Again, the Turing jump I'm going to start calling capital J. But it's just another, don't need it, I guess. But okay, so it's just A goes to A jump. We can do things like form finite iterates of the Turing jump, composing the Turing jump with itself finitely many times. You don't have to stop at finitely many iterates. So we can actually form what people call transfinite iterates, so iterates involving sort of infinite steps for any countable way of forming iterates. So this is for any countable ordinal, if you are familiar with ordinals. So let's just say there's sort of infinite iterates of the Turing jump. That makes sense. Above all of these things, I'll draw a picture in a moment, there's the hyperjump. So I'll define that very briefly later in the talk, which I'll call H. And this keeps going. So okay, these are my examples of natural Turing invariant functions. Maybe you were hoping for like examples coming out of I don't know, things that are more familiar, but no, they're going to come out of computability theory and beyond. Okay, so is there anything else? Definitely. So we can form, sorry, this is like rubbing this. I'll walk more carefully. Is there anything else? Well, we can form minor variations of the functions we've already seen. So we can do things like agree with the Turing jump except on some small set. So you can say, look at the function capital F that on input A outputs the jump of A unless you don't compute the jump already or something. So this is what we'll see in a little bit. That's going to be considered a minor variation of the Turing jump. So it's essentially the same thing as the Turing jump from the perspective we'll be interested in. Okay, what else? Well, we can form genuinely different functions if we get to use some well order of the power set of the natural numbers, which in reality has a well order. Okay, so using a well order of the power set of the natural numbers, we can exploit we can use the Kleene-Post theorem, exploit having access to a well order of the power set of the natural numbers, and do the following. On input A, we can just output the least in our well order set of natural numbers of intermediate degree between A and A jump. So that's going to be Turing invariant. It's Turing invariant because it only depends on the degree of A, right? If we plug in A and A stars A and C, and they have the same Turing degree, then the least thing in our well order that are between them will between A/C or A jump / C jump is this very same set. So using a well order, we can get genuinely different things from the things in my list by sort of exploiting theorems from computability theory, like the Kleene-Post theorem. So what's going on? And this is what we were saying before. So yes, there are examples of other functions. There is an example of a counterexample to this question of Sachs, kind of without this definability constraint. Okay. So again, what's going on in this last example is if we use a well ordering of the power set of the natural numbers, we can turn computability theory constructions that aren't Turing invariant into Turing invariant functions. Okay. But of course, this seems to essentially involve the well order. And this is what takes you out of the simply definable functions sort of world. So, for example, just a point. So, we don't really care about power set of the natural numbers, way of thinking about things. So we can move between sort of equivalent representations. So often I think I'll identify power set of the natural numbers with the reals, and then later we'll identify this with functions from the natural numbers to the natural numbers. Okay, so we can move between all of these things, and so, for example, we can import topological notions to studying the power set of the natural numbers. Okay, so in particular, well ordering of power set of the natural numbers is equivalent to, in some sense, a well ordering of the reals. Well, it's a theorem of Sierpinski that there are no Borel well orders of the reals. So it seems that we won't get Borel measurable functions if we describe them in a way that exploits access to a well order of the reals, or a well order of power set of the natural numbers. So just to remind you, so a set is Borel if it's a member of the smallest sigma algebra containing the open set, so closing under complements, countable intersections, countable unions. And a function is Borel or Borel measurable if the preimage of any open set is a Borel set, or equivalently if its graph is Borel in R squared. Okay, so the point is, if we restrict to the Borel sets, it doesn't seem like we can do this trick. Okay. So we're about to be able to state Martin's conjecture. So I'll just speed up a little. Okay, a cone. We've already seen cones secretly, but okay, a cone is the set of all sets of natural numbers above some fixed set of natural numbers. So for example, we can look at the cone above zero jump. That's just everything that computes zero jump. We'll also say a subset X of the power set of the natural numbers is Turing invariant if it's closed under Turing equivalence. So natural notion. So cones are examples of Turing invariant sets. Sets where you only the members, you only care about the members up to Turing equivalence, those are Turing invariant sets. So here's a fundamental theorem due to Martin. It's a consequence of what's called Borel determinacy. So every Turing invariant Borel set either contains a cone or is disjoint from a cone. So we'll start considering sets which contain a cone as large sets, and sets which are disjoint from a cone as small sets. So with this perspective, we get a natural ordering on Turing invariant functions, which is called the Martin order. So for Turing invariant functions on the Turing degrees, we'll say that f is Martin below g if the set of places where f of a is computable from g of a contains a cone. So it's the natural thing to do with this sort of kind of measure on largeness notion on Turing invariant sets. So f is below g, Martin below g if f of a is Turing below g of a on a cone. And similarly, it's equivalent to g if the obvious corresponding thing. So if they're outputting Turing equivalent values on a cone. Okay, that's the Martin order. Okay, so now we'll state the Borel version of Martin's conjecture, and we'll see the full version sort of briefly later in the talk. So here's the Borel version of Martin's conjecture. So it has two parts. First, every Turing invariant Borel function is either Martin equivalent to a constant function, so outputting values equivalent to some constant on a cone, or Martin above the identity, so f of a computes a on a cone. Okay, that's part one. And part two, the Martin order pre-well orders the Turing invariant Borel functions, which are Martin above the identity. So pre-well order means it's linear except up to equivalence, and moreover, it's a well order. So any subset of the order has a minimal element up to Martin equivalence. Moreover, successors in this pre-well order are given by composition with the Turing jump. Okay, so let me draw a picture for you of the Martin order under Martin's conjecture. So this is what Martin's conjecture sort of says the Turing invariant functions look like. So at the bottom, we have the constant functions. So this looks like a copy of the Turing degrees. So these are the constant functions. Above all the constant functions is the identity function. Immediately after that in the order is the Turing jump. Immediately after that is the Turing jump composed with itself, and so on. Immediately after every function that's not one of the constants and not the identity is strictly above the identity. And immediately after, wherever it is in the order, the next thing is the jump composed with that. So that's the picture. It's like a very concrete picture for a very concrete structure saying this is exactly what the Turing invariant functions are like. Borel Turing invariant functions are like. Okay. Any questions about that? Okay. Both parts are open, but there have been some partial results. You know, and sort of, I hope it's clear that Sachs's question sort of is about this, exactly this. It's a small instance of this in some sense. It's like about asking between it preserves Turing reducibility. Okay? And just, it's not important, but this does actually, uniformly Turing invariant things actually are order preserving. So it's, yeah, it is more general, ostensibly more general notion than uniform Turing invariance, and it's, I hope you find it more natural. And it turns out that it's going to be a more tractable problem. So for example, Slayman and Steele also proved that part 2 of Borel-Martin's conjecture holds restricted to the order-preserving functions. So it's not just for uniform Turing invariant functions, but in fact for order-preserving functions by a totally different proof from their proof for uniform, from Steele's proof for uniform Turing invariant functions. Okay. So what we did, so there, you know, for a long time it remained open whether part 1 of Martin's conjecture, the Borel version of Martin's conjecture, was true for order-preserving functions, and we showed this in our paper. So Petrikov tonight. Okay, so yeah, it does. Part 1 holds for. Part 1 of Borel-Martin's conjecture holds restricted to the order-preserving functions. So every order-preserving function is either constant on a cone or it's above the identity on a cone. So combining our results and the Slayman-Steele results gives a positive answer for the Borel-Martin's conjecture restricted to order-preserving functions. Right? They proved part 2, we proved part 1. Restricted to order-preserving. So again, the full conjecture is very much open. Okay, so that's the Borel version, and then I'm going to start talking about the full version of the conjecture, which does involve some more maybe unfamiliar ideas from set theory. So it involves the study of the axiom of determinacy, which I'll introduce in a moment. Okay. So why are we gonna go beyond the Borel functions? Well, the Borel-Martin's conjecture really just isn't satisfying. So the apparent structure on the natural functions of the Turing degrees is not limited to the Borel functions. It extends beyond the Borel functions. It's a very small part of the place where this phenomenon is seen to be happening. So, for example, it holds for the hyperjump, which I'm about to define, I believe, and its iterates. Okay, so the hyperjump, this is not going to be a non-Borel function. The hyperjump is a function of the right kind, so it's going from taking a set of natural numbers, outputting a set of natural numbers. So it takes A and outputs the set of all E, such that phi E sub A, so the program E which uses A as an oracle, codes a well order of the natural numbers. So again, when I say codes a well order of the natural numbers, we're not going to demand that that's the usual order of the natural numbers. We're just taking the natural numbers as a set, ordering it in some way specified by the ETH program using A as an oracle, and asking whether or not that's in fact a well order. And again, a well order is a linear order, but every subset of that order actually has a least element, like the usual ordering of the natural numbers. So codes for well orders of the natural numbers, really that's the same thing as countable well orders. So we're looking at sort of the set of all codes for countable well orders relative to A. Okay, this function is not Borel, but again, it seems that there's nothing intermediate between the hyperjump and the jump composed with the hyperjump. Nothing natural between those two things. So we want to look at what's going on even outside of the nice Borel realm. Okay, and just where this goes, so I drew the Turing jump and its iterates. These are all below the hyperjump. So the hyperjump is far above, far above the jump, above all of its iterates in the Martin order. And this is just the beginning. It's a very long, well-ordered hierarchy, which in some sense is still being discovered. Okay, so let me remind you the narrative of how I've been talking about this. So we focused on Borel functions because there was no Borel well-ordering of the reals by the Sierpinski theorem. So that was the sort of why this seemed like a good idea. But the modern set theoretic explanation for this fact, and really for the general good behavior of the Borel sets, is that they are determined. So what does that mean? So in every infinite, so this is not supposed to be something, a sentence that's easy to parse, so I'll draw a picture. In every infinite two-player game on the natural numbers with Borel payoff set, one of the players has a winning strategy. So what's the picture here? So we're considering a game, an infinite game, where players alternate playing natural numbers. So they're sort of allowed to see how the game has gone so far, and we say and we have some set of rules for the game, which we think of as a set X of functions from a set X of functions from the natural numbers to the natural numbers. Okay, so X describes who wins given the final output of the game. So we say, let's say 1 wins if this output, if the map I goes to Ni is a member of X. Okay. And again, I'm going to identify functions from this set with the reals and with powers for the natural numbers. Sorry if that's something that makes you uneasy. Okay, so that's what determinacy says. It says this game is determined, and X, this game is associated to the rules of the game, X. So I mentioned Martin's theorem, this theorem of Martin on containing a cone and being disjoint from a cone. That's a consequence of Borel determinacy, this statement that every game where the corresponding set X is a Borel set is actually determined. One of the two players has a strategy to play to win. Okay, so the axiom of determinacy, AD, asserts that actually in any game you play, whether or not the payoff, the set of rules is described in a Borel way, in any game at all, one of the two players has a winning strategy. So this contradicts the axiom of choice because it in fact implies there's no well order of the reals or power set of the natural numbers. Okay, but for reasons I'll get into in a little bit, the full Martin's conjecture is stated in this context under the axiom of determinacy. Okay, so it's stated more specifically, we still keep most of the axioms of set theory, the Zermelo-Frankel axioms, ZF. We drop the axiom of choice, but we're going to keep a little bit of choice. Doesn't matter what it is, but it's a weaker principle called dependent choice. And importantly, we add the axiom of determinacy. This theory, ZF plus DC plus AD, implies, as I said, there's no well ordering of the reals, but it also implies many other interesting things. So, for example, that all sets of reals are Lebesgue measurable. So it avoids many sort of unintuitive consequences of the axiom of choice, like the existence of a non-measurable set, and much more. Okay, so under ZF plus DC plus AD, Martin's theorem that we saw before actually just extends to all sets of all subsets of the power set of the natural numbers. So every Turing invariant set either contains a cone or is disjoint from a cone, assuming this theory. This Martin proved first. The other proof is hard. Okay, so similarly, the full version of Martin's conjecture just drops this Borel restriction under the hypothesis of ZF plus DC plus AD. Okay, so it looks just like this, exactly the same as before, but I should have just had the word Borel crossed out. I've just dropped that word from both part 1 and part 2. Okay. So, and I guess the picture remains the same, but now it includes things like the hyperjump and the J who goes with the hyperjump. Any questions? I know probably people are unfamiliar with AD. You don't need to, really get what it's about to, I think, sort of see what's going on. Okay, so why are we working? What does it mean to prove something from ZF plus DC plus AD? I think this is quite hard to communicate, but here's what's going on. So in reality, under ZFC, we have choice in the real world. Under ZFC, together with strong axioms of infinity, so these strong set theoretic hypotheses called large cardinal axioms, all reasonably definable functions, including the Borel ones, the hyperjump, and the iterates of the hyperjump, and things much beyond this, turn out to fit inside a model of this theory, which is moreover correct about simple statements. So it's correct about the relative order in the Martin order, for example. So all of the reasonably definable functions sit inside a model of determinacy where Martin's conjecture says the Martin order behaves as in the picture. Okay, so how do you interpret this as sort of consequence of this theory? Well, you interpret it as being a statement about all reasonably definable functions in a kind of delicate way, however. And again, of course, both parts are open. Slayman and Steele showed both parts actually for uniform Turing invariant functions. So the proof that works for the Borel sets also just works under AD. It's a determinacy argument. Okay, and our result on part 1 for order preserving functions also goes through to this context. So assume ZF plus DC plus AD, then part 1 of Martin's conjecture holds for order preserving functions. Okay, so again, we just dropped the word Borel from the theorem I displayed before. And again, you should think, again, you're supposed to interpret this as saying, if you restrict to these reasonably definable functions, Martin's conjecture, as long as they're order preserving, part 1 of Martin's conjecture holds. So every reasonably definable thing is, either constant on a cone or above the identity on a cone. Okay. So I'm not going to say anything about the proof except one comment just to introduce another idea. The way we proved this is by showing that order-preserving functions satisfy some other property that we'll call measure-preserving. That they are measure-preserving. And that part 1 of Martin's conjecture holds for measure-preserving functions in this determinacy context. So here's the definition. It's maybe slightly hard to parse just because of the way I wrote it. A function is measure-preserving, and I won't say why I'm calling it that, but okay. Is measure-preserving if, for any A, the set of B where f of B computes A contains a cone. So it's a sort of simple statement, and actually has an even simpler conceptual statement given what we've talked about. So a Turing invariant function, I should say, like, this definition makes sense even when it's not, f is not Turing invariant, but a Turing invariant function is measure preserving exactly when it's Martin above every constant function. So the measure preserving functions are Martin above every constant function. Yeah, I guess I have a small error. So we proved that order preserving functions that are not constant on a cone are measure preserving. Sorry about that. Okay. So yeah. So here's our theorem. So assume ZF plus DC plus AD, then every order preserving function which is not constant on a cone is measure preserving, is above every is above every constant function. If you're not constant, if you're order preserving and not constant on a cone, you're above every constant on a cone. And then, as I said, moreover, part 1 of Martin's conjecture holds for the measure preserving functions. What does that mean? Well, that just means if you're above every constant function on in the Martin order, then you're above the identity in the Martin order. Okay. Let's see. Oh, I have a lot of time. Great. Okay. Any questions about this definition or the statement? Sorry about the small mistake. I hope that didn't confuse you guys. Okay. I do just want to say, I think the way I organized this, right? I was emphasizing interest in the order preserving version of Martin's conjecture. Martin's conjecture restricted to the order preserving functions, but I really think this second result that part 1 holds restricted to the measure preserving functions is really interesting on its own. So if you again look at this characterization on the bottom here of measure preserving functions, it's something that's purely described in terms of the Martin order. How a function is measure preserving just depends on its place in the Martin order. Just depends on its place in the Martin order. So it's somehow like a structural fact about the Martin order restricted to the Martin order on all Turing invariant functions. If you're above every constant function, you're above the identity. Results like that have been like really elusive, and if it's not clear, right, part 1 and part 2, the full part 1 and part 2 of Martin's conjecture are results of that flavor. They're genuine structural results about the Martin order. And I think, I don't know, it's debatable, but in some sense this is sort of the first structural result of the Martin order that doesn't have some kind of definability or explicit definability consideration built into it, or alternative hypothesis like uniformity or order preserving. So I think this is quite an interesting result. Okay, so I have just a few minutes left. So these results are the main theorems from our paper, which I didn't tell you the title, but it's part 1 of Martin's conjecture for order preserving and measure preserving functions. So quite literal title. And I just want to mention that I think there's a lot of interesting stuff that there is to do here. So I think one interesting thing is to try to get more results like this measure preserving result. Don't just try to start out just getting in some kind of, don't just go for Martin's conjecture, but figure out anything else at all that you can say about the Martin order on Turing invariant functions. functions, on all Turing invariant functions. Yeah. And then the other thing that I think is interesting to do is try to do more with order preserving functions. So I mentioned that the Slayman and Steele proved part 2 for order preserving functions that are Borel. Okay, maybe you noticed I didn't mention that this holds. That's a theorem where we can't just cross out the word Borel under AD. Okay, so part 2 of Martin's conjecture beyond the Borel for order preserving functions beyond the Borel functions is actually open. A little bit about it is known. So actually, in that same Slayman-Steele paper, they combined their work with a result of Wooden and showed the following. So I mentioned the hyperjump. Remember, this was this function h spitting out codes relative to the input for countable well orders. So Slayman and Steele, together with Wooden, showed that every order preserving function, in this AD context, every order preserving function is comparable to the hyperjump, so either below it, equivalent to it, or above it. And moreover, if you look at part 2, if you look at the things between the identity and the hyperjump, they satisfy, that are order preserving, they satisfy Martin's conjecture. So they sort of proved order preserving Martin's conjecture up to the hyperjump. Okay, and that was the best that was known since their theorem. And again, this is something Patrick and I have been working on. So we were able to extend this to something that doesn't seem so exciting, maybe the double hyperjump. So even doing that was involved quite new ideas. So here in this theorem, we have the way I said the previous one, right? It's order preserving part 2 up to the double hyperjump. But somehow going from the hyperjump to the double hyperjump was really difficult. I mean, not so difficult, but it required new ideas. And we've been able to do this for iterates of the hyperjump more generally, and in fact, as of recently, a little bit beyond. But doing it completely in general seems like a very, very difficult and interesting open problem. So again, I think a really interesting question is prove under this deterministic context order preserving part 2 of Martin's conjecture for order preserving functions. Okay, thanks.
Thank you, Benjamin, for a very nice talk. Are there any comments or questions? Yes.
So for this hyperjump result, doing a lot of coding to make them figure out where you're doing motion. Is there anything that's reliable on making a choice?
No, yeah, I mean, no, definitely it doesn't rely on any choice. Yeah, I mean, the specific definition of the hyperjump, I agree. It seems so like I was coding ordinals by like programs, but no, it's a quite flexible thing. If you make any reasonable thing, it all gives you the same thing. Very reasonable question, though.
Are there any other questions? If not, let's thank Benjamin again.